Hello. In this video, we will be discussing Lab 3 Black Hole Orbit. The object of this lab was to find the mass of a black hole through the analysis of a computational model of an orbiting star's position and motion data. Unlike previous labs, we are not going to predict an object's motion. Rather, we will work backwards in analyzing the star's motion relative to the black hole that it is orbiting to calculate the mass of the black hole, which was found to be about 5.1714 times 10 to the 31 kilograms. In order to compute the mass, both the law of universal gravitation as well as the momentum principle were utilized for the calculations. The law of universal gravitation states that any two objects in the universe are attracted to each other through a force proportional to the product of their masses over the square of the distance between the objects, all multiplied by the gravitational constant. The gravitational constant for all objects in the universe is about 6.67 times 10 to the negative 11. Using the given initial mass of the star, the gravitational constant, the distance between the star's position in the model and the given position of the black hole, in addition to the net force found using the Python code, the mass of the black hole was calculated by rearranging the formula given by the law of universal gravitation to compute unknown mass. Furthermore, the momentum principle was first used to calculate the net force. The momentum principle, in its derivative form, states that dp over dt equals F net. Essentially, breaking this down signifies that the change in momentum over the change in time, or the derivative of momentum over time, equals the mass of an object times the derivative of the object's velocity, which equals the object's mass times its acceleration, which also equals the net force acting on the object. This formula was used in the code as a means of deriving F net from dp dt. F net would then be part of the formula to obtain the mass of the black hole. The initial conditions included the mass of the star, 4.3773 times 10 to the 27 kilograms, the time step, or delta t, 86,400 seconds, or 1 day, and the position of the black hole at 4 times 10 to the 10, 0, 0 meters. And the motion of the black hole was assumed to be stationary without any change in its position. This data was input into the code at the beginning. Later in the code, the position data of the star was analyzed by the code so that it could be used later to computationally describe and calculate the star's motion, such as its velocity, which is shown here. The main portion of the code, which was edited to and significant in terms of physics principles, is under the second while loop. Here, the star's initial and final velocities were obtained, which were employed to get its initial and final momentum, mass times the star's velocity at the given time. The change in the star momentum and delta t were used here for the star's dp dt, and according to the momentum principle, also its F net. P hat, or the direction of the momentum, was determined by the momentum at the given time divided by its magnitude. Then the magnitude of the change in momentum over the change in time shown here, multiplied by p hat, gave the parallel component of momentum, which by the momentum principle again equals F net parallel. Lastly, F net perpendicular and dp dt perpendicular were found by subtracting dp dt parallel from dp dt, since the sum of both components of the change in momentum equals the total change in momentum. The last section of code shows how arrows were inputted into the computational model. 3 arrows, each respectively standing for F net parallel, and F net perpendicular, were used to visually depict the change in direction of these forces and component forces during the motion of the star. Here, F net, represented by the yellow arrow, seems to point in the same direction and in the same magnitude throughout the entire motion of the star that was analyzed. The blue arrow, F net perpendicular, changes along with the motion of the star as it points towards the middle of the circle, or basically towards the black hole. Finally, the black arrow, or F net parallel, has the smallest magnitude and points in the direction of the star's motion. The main point of the code was also to quantitatively find its net force and radius as seen in these two print statements. The radius of the orbit, or the distance between the star's position and the black hole, was calculated by finding the magnitude of the distance between the star position at the given time and the black hole position that was already given to us. Now, these values can be plugged in to the rearranged formula, m equals r squared times F net divided by the star's mass times the gravitational constant, equaling about 5.1714 times 10 to the 31 kilograms. Now on to the questions. Although Fnet and its parallel and perpendicular components numerically equal dp dt and its parallel and perpendicular components, as shown in the equations below, they are different in how they are derived. Fnet is essentially derived using the law of universal gravitation, while dp dt is found using an object's velocity to find momentum, and later the change in momentum over change in time to equal dp dt. Moreover, Fnet can directly affect the motion of the object, while dp dt simply describes the motion of the star. It would not be possible to find a new mass of a black hole other than the one that we just calculated if the star that was orbiting it had the same motion as in this lab, because that would basically mean that the star's positions are the same as before, which could not give a different Fnet for a different black hole mass. There's no other mass that could have the same motion data from the same star other than the one calculated in this lab. Thank you.